Welcome to a lesson on surface integrals where the surface of integration is a parameterized surface. If we have a smooth surface given by r of u v and f is a continuous function, then the double integral of f integrated over the surface s with respect to s is equal to the double integral in the uv plane as we see here if we write the function f by replacing x with x of u and v, y with y of u and v, and z with z of u and v. And differential s is equal to the magnitude of this cross product, differential a, where differential a is either du dv or dv du. And in the video on area of a parameterized surface, we discussed where this extra integrating factor came from when converting from differential s to differential a, and it comes from the area of a very small tangent plane. And before we take a look at an example, I want to emphasize here that this video only focuses on surface integrals where the surface is given as a parameterized surface. I have a couple other videos that show how to evaluate a surface integral when the surface is given as z equals g of x, y, as we see here. Notice that if this is the case, differential s is replaced with this integrating factor times differential a. So let's take a look at our first example. We want to evaluate this surface integral using a parametric surface where our function is x times y and our surface is x squared plus y squared equals 4, and z is on the closed interval from 0 to 8, only in the first octant. So let's first parameterize our surface. Because this is a cylinder, we'll use cylindrical coordinates. So we'll let x equal 2 cosine u, y would be 2 sine u, and then z would just be v. And because we're in the first octant, u is going to be on the closed interval from 0 to pi over 2, and v will be on the closed interval from 0 to 8. So let's work on determining the magnitude of this cross product. So let's go ahead and find the partial derivative of r with respect to u. That's going to be negative 2 sine u, 2 cosine u, and 0. Then the partial derivative of r with respect to v, that'll just be 0, 0, and 1. So to determine the cross product of these two, we'll evaluate a 3 by 3 determinant where the first row is ijk, the second row will be negative 2 sine u, 2 cosine u, and 0. The row will be 0, 0, and 1. Now I'm going to go ahead and evaluate this using the diagonal method. So I've already copied the first and second columns on the end. And now we'll sum the product of these three diagonals, and then we'll subtract the product of these three diagonals. That'll give us our cross product. So we're going to have 2 cosine ui plus 0, minus 0, minus 0, and minus a negative 2 sine uj. So it'll be plus 2 sine uj. So now let's go ahead and determine the magnitude of this cross product. So 4 cosine squared u plus 4 sine squared u. Now if we factor out the 4, we're going to have cosine squared u plus sine squared u. That's equal to 1. Well, the square root of 4 would be equal to 2. So let's go back and take a look at the problem again. All that work gave us this magnitude equal to 2. And now we're going to rewrite our function x times y as a function of u and v, where x is equal to 2 cosine u and y is equal to 2 sine u. So we'll have 2 cosine u, 2 sine u times 2 differential a. So again, x was equal to 2 cosine u, y was equal to 2 sine u, then we had the magnitude was equal to 2, And then for differential a, let's go ahead and write this as dv du. Remember, v was on the closed interval from 0 to 8, and u was on the closed interval from 0 to pi over 2 because we're in the first octant. So remember, our function was equal to x times y. That's why we have 2 cosine u times 2 sine u. Okay, so let's go ahead and pull out the 8 and start to integrate. Integrating this back to v is just going to give us v times cosine u sine u. Replacing v with 8, we'll have 8 cosine u sine u minus 0. So we'll have 64 cosine u sine u. Now here we'll perform a substitution. Let's go ahead and let w equal sine u. So dw is going to be equal to cosine u du, which is good because all of this will be dw, and this will be w to the first. So that'll give us w to the second divided by 2, or 64 times 1/2 w to the second, where w is sine u. And then the sine of pi over 2 is 1. 1 squared is 1, minus sine of 0 is 0. So it looks like we have a value of 32 for our surface integral using a parameterized surface. I think we'll stop here on this video and we'll take a look at a second example in part 2. Thank you for watching.